Okay, let's continue our discussion of this inverse function business. Last time we did find the inverse function for f of x equals x cubed plus 2. And what we found is its inverse function is indeed cubic root of x minus 2. We want to have a little bit more discussion about this function and it is its inverse. And what we want to do is we want to illustrate the graph of the inverse function and the original function. In this particular example, the original function is x cubed plus 2, and we want to say we want to look at what the inverse function, the graph of inverse function look like. And before we go to before we draw the inverse function for this example, let's look at a more general picture. So we know the function f of x, okay? So a more general term here, this is x and y, and we separate it by the line of y equals x. So suppose we have one point AB on graph of f of x. That means f of a equals b. All right, and then what about the inverse function? So if y equals f inverse, and then for the point AB, we notice the b should be the output of this f of x when we evaluate this f at a. So the corresponding inverse should be set up like this. So now we choose the b as the input of the inverse function f inverse, and the output of this f inverse should be a. Okay, so now what? So if we have a point A, B here, and then this point will be on the graph of f of x. And similarly, if you look at the other point, well, the point BA will be on the graph of f inverse. And this AB and BA points will be symmetric about the line of y equals x. So now we see the graph of the function will be symmetric to the graph of its inverse. All right, so this is what we want to discuss. All right, you can think about how to draw the graph of the inverse for this particular example. Just think about how to make it symmetric about this line y equals x. I guess it's more like this. So this is f of x. This is f inverse of x equals cubic root x minus 2. Okay, so now we want to continue our discussion to this logarithmic functions. Why we want to discuss the logarithmic function after the inverse function? Well, we have a very good reason, because if you remember, we discussed the exponential function f of x equals a to the power x with base a bigger than 0. And we say if a is not equal to 1, then we have its inverse of this exponential function to be the logarithmic function. Okay, so here, remember, we want to use some abstract notation so we can manipulate. So here we have f of x equals a to the power x, that is the exponential. And what is the inverse? And the inverse of this exponential function will be log a of x. Okay, so now we should see f inverse is log a. Okay, and we said it should be equal to y. And because we have this f inverse of x equals y, it is the same thing as we say the exponential of y equals x. Okay, because here this part is f of y, sorry, f of x equals y. All right, so now we can continue our discussion with the property of the logarithmics. So first of all, we want to discuss a little bit of this logarithmic and exponential cancellation. Um, People always say that, but the reason for that is that we have this so-called law of cancellation, right? If you still remember, the law of cancellation tells us the f inverse of f of x equals x, and f of f inverse equals x. And here, this x is in domain of the function f, and this x is in the range of the function f. All right, so this is very important because as we discussed earlier, this log a is supposed to be the inverse. And for this a f of x equals to the exponential function. All right, so now you can see this is the f of x, this is the f inverse of x, so that is why we have x as the output of the cancellation result. So now we want to also pay attention to the value that you can put in for the logarithmics. If you remember, the graph of the exponential function look like what? Look like this, right? Okay, the range of the exponential function are just bigger than 0, right? So all the a to the x will be bigger than 0. Okay, so that means the logarithmic function can only choose a value that is bigger than 0. So the input of the logarithmic function, which is the output of the exponential function, has to be bigger than 0. So this is what we notice here. But the input for the exponential function will be could be any real number. So that means the output of the logarithmic function could be any positive or negative number. So this is the second part of the law of cancellation tells us. Okay, so this part, this is f of f inverse of x, which equals x. Okay, so this is a pretty abstract result, and we have to try to understand it a little bit further so we can actually apply this. But another way to is to just practice a little bit by using those concepts, and particularly we want to remind us about some of the law of logarithms. And here we have to say there are a couple of things. If both x and y are positive, well, in some cases, This x and y, can x, y be negative? No, because essentially both x and y are showing up as the input for the log. So all of them have to be positive. Otherwise, this log function cannot be evaluated. Okay, so what is the first law? The first law is this. So for example, log 2 3x equals what? It equals log base 2 3 plus log base 2x. All right, and then similarly, log 2x over 4, what is this equals? This is a log 2x minus log 2 4. And here, this is an interesting one. X to the power 1/2, what is this equals? Remember, here, this 1/2 is indeed the power of x, so we can move this 1/2 to in front of the logarithm. And similarly, if you have log 3, but 2 to the power of negative x, let's say, and then what? Then if x is any real number, what we can do is we can write log base 3, 2. All right, and one of the important fact about the logarithmic function is that here we say the base a cannot be 1. Well, that is for sure, because when we define this logarithmic function, we said a cannot be 1. But if we choose this base to be some special number, just like the natural exponential function, all right, so recall, the natural exponential function is e to the x, right? Okay, so for corresponding to that, we have this natural log function, which means the base is indeed e, and we use this notation to simplify it. So here, the f of x is natural exponential, and f inverse of x is indeed natural log of x. And obviously, we can still use the law of cancellation. So here, this is f inverse of f of x, so that should be x. All right, so this is the first result here. And for the second result, well, this is another law of cancellation, right? So this is f of, because the log of natural log x is indeed f inverse of x here, so it is x. And obviously here, this x could be any real number. All right, but this x here has to be bigger than 0. All right, and from this result, well, from which result? From this result, we can see when x equals 1, what do we have? When x equals 1, log e equals just 1. Okay, so now let's do another example to practice our understanding of logarithmics. So here, if we are facing this problem, we want to solve for x. How do we do it? Well, obviously, this is an exponential function, and there is a natural exponential function with the exponent involve the x. So what we want to do is to actually so-called apply the natural log to both sides, and then we'll see what will happen. So if we do that, we take a natural log on the left-hand side, and we have to do it for the right-hand side also. Okay, so on the left-hand side, we can use the law of logarithm, right? Because here, there's exponent. We can move this exponent in front of the log, which is 5 times 3 minus x, natural log e equals natural log 10. Another way to think about the left-hand side is to use this law of cancellation, right? Because as we recall, the log of e to the x equals x, all right? And here we just replace this x by 5 minus 3x. So this tells us the same thing, because the left-hand side over here is indeed 5 minus 3x. So what is x? So we move this to the left and move this to the right. So we get a 5 minus log 10 equals 3x. So x equals 5 minus log 10 over 3. So this is our answer. So now we just have to realize when you try to solve something that is on the shoulder as an exponent, you have to move it to on the floor so that you can handle. We know the log and the exponential are fancy and useful, but in terms of calculation, it's better to just treat it on the floor instead of as an exponent. Okay, so now what? Now we can deal with this seemingly complicated example, and we want to write this as a simple logarithm. Can we do that? Well, I think we could, right? Because we have 3 different log that we can use. So how to do this? So for the first term, we notice the law we want to use is log, well, x to the power r equals r times log, right? And we have to use it from the right-hand side to the left-hand side. So that means the first term is log a to the power 3, right? Similarly, for the second term, we make it a plus because we want to move this negative 1/2 to the exponent to the shoulder of this b. And then the last term will be kept the same. And then what? Because we have another rule or law we can use. All right, so the sum of the 2 log with the same base is the log of the product of those 2 numbers. All right, so this is the log a to the power 3 times b to the power negative 1/2 and the time 2c. So this is our answer. Okay, so we already noticed that we use natural log a lot, but what will happen if we do have log with the base that is not a natural number? Okay, so here's the result we can use. So for any log with base a, we can actually make the change. We can change it. We can represent it by using the natural log. That seems to be interesting, but I think we can actually prove it. So how to do that? So let y to be log with base a x. So remember, the natural log is the log function is the inverse of the exponential function. All right. So what does that mean? That means if we do consider the inverse of it, all right, then we get this. So here, this is f of x equals y, right? And here we have f inverse of y equals x. The same thing. Or if you treated it as y equals f inverse of x, and then this will be f of y equals x. Same thing, whether which one you treat as the inverse of the other, depending on what you want to start with. Okay, so with this, what will happen? You can take the log, you can take the natural log of this equation on both sides. What you have is natural log a to the y equals natural log of x. Remember, now we can use the law of logarithms, right? So this becomes y times natural log of a equals natural log of x. So this tells us y equals natural log of x over natural log of a. Remember, when we first start this question, we let y to be um, log base a x. Okay, so now what? Now we want to just point out the last fact about the logarithmics and the exponential function. As I said earlier, the function and its inverse are having their graphs to be symmetric about y equals x. All right, so for the natural log function, we have the graph like this. And the exponential function is relatively easy. So this is the one, this is the one. And if the exponential function is always increasing and intersecting the vertical axis at 0, 1, and the graph of the logarithmic function, natural logarithmic function, looks like this. And so you can see when x approaches 0 from the right side, the natural log will go down to the negative infinity, right? And the natural log function will intersect this horizontal axis at 1, x equals 1. All right, so now we can stop this part of the video.